Good morning guys. So in previous lecture we started the new concept, means finite elemental FEA procedure to truss element. Okay, so in previous lecture we tried to derive the elemental stiffness matrix for truss element, but we left at this step. Actually we concluded our lecture due to this time calculations. We concluded our lecture here at this stage, or at this step we concluded our lecture. Now from this step we will try to solve this, try to simplify these matrices, and finally we will get the global stiffness matrix or elemental stiffness matrix for this truss element. Okay, so for this we need to multiply, or for this we need to simplify these two matrices. Let's do the multiplication of these two matrices, then finally multiplication of these two matrices. Okay, so as we know that we proceeded from the basic of the truss structure. So from that we have actually first we concluded that this is your nodal displacement vector, which is nothing but nodal displacement vector in terms of global displacement vector. Okay, this is equal to u, small u is equal to this matrix L into this is your global vector or global coordinates. Okay, similarly we have written from this equation this force and displacement relationship, or we can write these forces in terms of this nodal forces in terms of global forces. Okay, and finally as we know that this is the L matrix. L matrix is, it is nothing but L M 0 0 0 0 L M, where L is nothing but your cos theta and M is nothing but your sin theta. Okay, so in this way we have derived this matrix also. So now in previous lecture we concluded our lecture at this step. Now we will simplify this step and we will get our elemental stiffness matrix. So to simplify this step, so first we need to multiply these two matrices. Okay, so this is first matrix and this is second matrix. So multiply these two by multiplication of these two matrices we will get one matrix. So K equivalent will become, so K equivalent will become, this is the transpose of this L matrix, actually L 0 M 0 0 L 0 M into A by L into, now so multiplication of these two matrices. So this row multiplying by this row to each column of the second matrix. So by multiplying this row to this column, so 1 into L, L plus minus 1 into 0, 0. So L plus 0, L. So first will become L. Now second, this matrix, this row into second column, minus 1 into M, M, minus 1 into 0, 0. So 1 into M plus 0, it will become M. This row into this column, it will become 1 into 0, 0. Minus 1 into L, minus L, minus L. Then this row into last column, so 1 into 0, 0, minus 1 into L, minus L, minus L. So actually it should be a 2 row 4 column matrix. Okay, 2 row 4 column. Then now next is what? Multiply by second row to all these columns. So this row minus 1 into this L, minus L, because minus 1 into L, minus L, plus 1 into 0, 0, minus 1 into M, minus L, plus 1 into 0, 0, minus L, then minus this row into third column, minus 1 into 0, 0, 1 into L, L, then minus 1 into 0, 0, L into M, M. Okay, actually this derivation it can be asked in your exam, in semester exam or in semester exam for 6 to 8 marks. So that's why you need to just simplify these two matrices. After this you will get this matrix. Now multiply this matrix to this matrix. Okay, then finally we will get the element stiffness matrix. So after multiplication of these or simplifying these two matrices, you will get this matrix. Now we will do the multiplication of these two matrices. You will get final element stiffness matrix for this truss element. Okay, so K equivalent to become A by L is common into, okay, so this row into this column means multiplying by this row to all these columns. There are 1, 2, 3, 4 columns. Okay, so there are 4 rows. 1, 2, 3, 4. So multiply these row to these column. So L into L square means this row into this column. What is the output for this row into this column? L into L plus 0 into minus. So output will be L square. First row into first column, output will be L square. So we will write L square. Similarly, first row into second column, what will be the output? So first row into second column, L into M plus 0 into minus is 0. So output will be L. So second is L. Next, first row, third column. So L into minus L square plus 0 means it will become 0. So my L into minus L. Similarly, this row into this column it will become 0. Due to this 0 into M it will become 0. So only L into minus L is minus L. Minus L. Then second row into first column. M into, due to this 0 there will not be any effect for second parameter or second number actually. So M into M. So this row into this column. So M into L, ML or LM. Due to this 0, there is no effect. This row into this column. M into M square. Then this row into this column. Minus LM. This row into this column finally minus L square. Now here first one is 0. So second is the main effect. So first one is negative. So this row into this column. So 0 into L, 0 plus L into minus L, minus L square. Minus L square. This row into this column. 0 into L, 0. L into L, minus L. Minus L. This row into this column. 0 into minus L, 0. L into L, L square. Similarly, this row into this column, 0. L. Now this row into this column, 0 minus L. This row into this column, 0 minus L. Then this row into this column, 0 L. Finally last 0. This row into this column. So 0 into M minus L, 0 plus M into L. So finally you will get the elementary stiffness matrix for truss element. Okay, so this is K equivalent where, so K equivalent, finally K equivalent is A by L. This is a 4 by 4 matrix actually, and look at this. So this is the final matrix. So look, this is a symmetric matrix. This is a symmetric matrix. Okay, symmetric. Look, minus L square minus Ln, minus Ln minus L square, minus L square minus Ln, minus Ln minus L square. Then Ln, here is also L. Here Ln, here is also L. Means this is a symmetric matrix. This is a symmetric matrix about this diagonal n square, n square, n square, n square. So every matrix or every stiffness matrix, it should be a symmetric matrix. So here, this actually we have discussed these things in our first unit. Means every elementary stiffness matrix should be symmetric. Okay, so here this is the conclusion of that statement. Okay, so you will get here the symmetric matrix. So finally, you will get K equivalent is equal to A by L. So how to remember? If you start with L square, L square, M square, L square, M square. Okay. Then L square, Lm minus L square minus L. This is diagonal L square, L square, L square, L square. Row L square, L minus L square minus L. Or you can remember by using this symmetry. Minus L square minus L minus L minus L. Simply you can write here minus L square minus L minus L minus L square. Okay. And remaining here is the L. So here also L. And in this way you can remember. Okay, so this is the elemental stiffness. Actually, this is your elemental stiffness matrix for truss element, where A is the area of that element, E is the times modulus of that element, L is the length of that element. Where L, small l is nothing but your cos theta, small l is nothing but your sin theta. So where theta is what? This is the angle that we have taken from the global coordinate system or from the reference coordinate system. Okay. So if this is a structure, suppose there are three elements. If you want P is acting vertically downward direction, okay. So here K equivalent for A, E, L. These are the material properties, area, angulars and length for that, for each element. Okay. L is cos theta, M is sin theta. Where theta is what? Theta is the angle which is made up by that element from reference or from coordinate, global coordinate system. So for this element, this is the theta. Now for second element, what will be theta? Actually second element, this second element it is parallel to the x-axis, global x-axis. This is global y-axis. For this third element, this is the angle. Means from this element, it is at angle theta from the reference x-axis. So this is your theta. This is the anti-clockwise direction. So if you are taking anti-clockwise direction, or you are taking the value of theta in anti-clockwise direction, then it should be positive. But suppose if there is a one element like this, let us suppose if there is a one element like this, then if you take theta from this or in the clockwise direction, then it must be, this theta must be negative. So anti-clockwise direction, if you are taking theta value, it should be positive. If you are taking in clockwise direction, then it should be negative. Okay, so whatever, because such type of examples will occur if we are going to try, we will solve such type of examples also. So here this theta value should be positive because we are getting in a anti-clockwise direction. Now for second element, so for second element, what will be the theta? Actually this second element, it is parallel to this reference x-axis. Okay, this element actually it is inclined with angle theta, but this element it is parallel to this x-axis. So theta must be 0, or theta 2 must be 0 for second. This is your theta 3. Now third one is theta 3. Theta 3 we have hold on. Theta 2 it is 0. Now theta 1. So theta 1 from this reference axis, it is from this figure it is equal to actually 90 degree. So theta 1 is equal to 90. Okay, so in this way we can calculate the value of theta. Okay, so how to find out the values of theta? Now here they have given only the coordinates. This is 0, 0. This is 100, 100, and this is 0, 100. So how to find out the value of theta? By using these coordinates. So as we know that this is the basic thing that actually you know that by using the Pythagorean theorem you can find out the value of theta. So first, for this case, suppose this is the example. Let us consider this one as an example. This is the reference x-axis, reference y-axis. If it is not given in the example, then we need to make one point, or we need to plot this xy system at any one node. Means at any node we need to plot this xy coordinates, xy coordinates, and from these coordinates we need to find out the thetas. Okay, so this is xy. Suppose let us they have given the coordinates like 100, 100, and this is 0, 100, and this is first one is 0, 0. So how to find out the values of theta? Suppose this is first element. Okay, this is first element. This is second element. And this is third. So we need to find here first. First we need to find out length, because we need length, as we know that for elemental stiffness matrix we need AE by L in bracket this matrix, where in this matrix we also need L is equal to cos theta and M is equal to sin theta. So we need, what is the requirement? L, we need length, we need theta. Okay, so first we need to find out length, then we need to find out theta. Or suppose these are the elements. So for element 1, for element 2, and for element 3, what are the lengths? Theta. Then from this theta we can calculate small n. N is equal to cos theta and n is equal to sin theta. Also from this values of L and N we can find out the values of ln, L square and L square. Why? Because in elemental stiffness matrix these terms occurs, L square, M square, ln. Okay, so we can simply make one table. Okay, so simply we can make one table which will include, first one is elements. For first element, what is the length, what is the theta, what is cos theta, sin theta, what is ln, L square, M square. Similarly, we will find out for second element, all same things will be calculated. For third element also we will find out L theta, cos theta, sin theta, ln L square, m square. Because all these things we need to formulate our elemental stiffness matrix for each element. Okay. So for example, let us say for this example, first we will try to solve the L theta, then cos theta, sin theta, ln L square, m square. Okay. So for first element, what is the length? Here only coordinates are given 0, 0, 100, 100. So in various types of examples, actually in general, in all examples, length is given. You need to first find out the theta, means length of all these three elements is given. But if it is not given, then they will mention the coordinates of the node. These are the nodes: first, second, and third. Okay. So if it is not given, they will mention the length. If length is not mentioned, they will mention the coordinates. From this given data, we need to find out the value of theta. So we need to find out the value of theta here from this figure. So we know that this is your x1, this is your y1, this is your x2, this is your y2. So how to find out length first? Okay. So how to find out length? As we know that this is a rectangle. So this will become your hypotenuse. So hypotenuse means what? This y. Suppose this is distance y and this is the distance x. Then hypotenuse, this L. L1 will become L1 square is equal to x square plus y square. So L1 will become square root of x1 square plus y1 square. Okay. Now this x1 is nothing but this x is nothing but this coordinate minus this coordinate. So this coordinate is what? 100. 100 minus first coordinate 0. So 100 minus 0, 100. So we can formulate this formula. We can write this formula as, so L1 it will equal to x square plus y square actually. X square plus y square. But x is what? X is what? This coordinate minus this coordinate. So x2 minus x1 bracket square plus y coordinate is what? Y2 minus y1. So y2 is what? 100 and y1 is what? 0. So y2 minus y1. So in this way you can find out length. Now length is known. Now find out theta. So to find out theta, we know that actually tan theta is given as tan theta. We know the value tan theta is equal to front side y, adjacent side. So front side y divided by adjacent side x. Or you can use sin theta cos theta to find out these values. So as we know that if we know this value y, or if you know this value L1, then we can take cos theta is equal to adjacent side means x divided by L1. X is known, L1 is also known. Then you can find out theta cos inverse of x by L1. So in this way you can find out theta for each element. Now this is first element, this will be your theta. For second element it is parallel to the x-axis. So theta 2 will be 0 and theta 3 actually it is 90 degrees. Theta 3 is equal to 90 degrees. So in this way you can find out theta 1, theta 2 and theta. Similarly L1, L2, L. If theta 1, theta 2 and theta 3 is known, then you can find out L. Similarly N. And in this way L square, M square. So in this way you can proceed to get this table. By using this table you can find out or you can calculate the elemental stiffness matrix for this first element. Okay, so elemental stiffness matrix for first element will become elemental stiffness matrix for first element. It will become A1 E1 by L1. These are the material properties which have mentioned in the example. L1 actually we have calculated into L square Lm minus L square minus Lm. In this way you can find it. Okay, so this is K1 or elementary stiffness matrix for this first element. Similarly, you need to find out elementary stiffness matrix for this second element, which is nothing but K2. And similarly, you need to find out elementary stiffness matrix K3 for this third element by using different material properties and by using L, M, L square, M square for this theta 3. Because L, M, L square, M square, Lm, these are the different for different elements. Okay, because they are depending on this theta 1, theta 2, theta 3 values. So you will get 3 different elementary stiffness matrices. Then 3 different elementary stiffness matrices. Now, what will be the connectivity of this first element? Now, actually we need to globally add these 3 elementary stiffness matrices finally. So first, what will be the global connectivity between these global connectivity of this element between these 2 nodes? So for first node we know that in x direction there is u1 displacement, in y direction there is v1 displacement. Similarly, for this element u2 is the displacement in x direction and v2 is the displacement in y direction. Okay, so this matrix finally by calculating you will get this 4x4 matrix. So connectivity of this matrix for this first element, it should be u1 v1 u2 v2 u1 v1 u2 v2. Similarly, the connectivity of this elementary stiffness matrix for this second element, what will be the connectivity? So the connectivity for the second element. Similarly, for second element there is u2 v2. Similarly, for third node there must be u3 horizontal displacement and v3 vertical displacement. So for connectivity, for second elemental connectivity, we will get the matrix after the calculation of simplification. We will get this matrix 4x4 matrix. This is nothing but your, or because for each element you will get 4x4 matrix. For each element you will get 4x4 elemental stiffness matrix. So connectivity of this second elemental stiffness matrix, it is in between u2 v2 u3 v3. So connectivity will be u2 v2 u3 v3. Similarly, u2 v2 u3 v3. Then connectivity for this third one, the connectivity is between node 1 and node 3. So it will become u1 v1 u3 v3. So this is it. We simplify, or we will get this third matrix 4x4 or 4x4 matrix. Then connectivity should be u1 v1 u3 v3 u1 v1 u3 v3. Now we need to add these 3 matrices globally, as we did the construction of global stiffness matrix during our spring as well as bar element. Similar way we will construct our global stiffness matrix. So as we know that as there are 3 elements, okay, 1, 2, 3, and for each element or for each node, as there are 3 nodes, so global stiffness matrix or what will be the order of global stiffness matrix? So as there are 3 nodes, as at each node there is a horizontal movement as well as vertical movement. For second element there is a horizontal movement as well as vertical movement. For third node also there is horizontal movement, third vertical movement. Means at each node there are 2 degrees of freedom. Okay, so look. So try to, so as in previous lectures, in previous for your spring system or your bar system, at each node there is only one movement in horizontal x direction. Okay, but for truss element, so at this node there are two movements. First one is in horizontal direction, second one is in vertical direction. It means that there are 2 degrees of freedom at each node. In previous case for bar element, there is only 1 degree of freedom at each node, but in case of truss element, as we know that we have converted this globally, so there are 2 degrees of freedom. First one moment in x moment of this displacement in x direction, or displacement moment in y direction. So at each node there are 2 degrees of freedom. So means at this node 2 degrees of freedom, at this node 2 degrees of freedom, at this node 2 degrees of freedom. So the order of that global order of global stiffness matrix will become number of degrees of freedom per node into, actually this is the standard formula. If we apply this formula to spring or bar, you will get same answer. Okay? So number of degrees of freedom per node into number of nodes. This is the order of global stiffness matrix, and this is standard formula to find out the order of global stiffness matrix for any system. So if we take the spring system, as we know that for spring system at every node there is a horizontal movement in x direction, so there must be only 1 degree of freedom. So 1 degree of freedom into number of nodes n. So order will become n. N is what? Number of nodes. But in case of truss element, we know that there is a horizontal movement as well as vertical movement. So there are 2 degrees of freedom at each node. So the order of global stiffness matrix for this truss element will become number of degrees of freedom per node. There are 2 degrees of freedom per node into number of nodes means n. So it will become 2 times n, means 2 times number of nodes. So order of your global stiffness matrix will become 2 times number of nodes. Okay. So this is clear. I think this is clear. So as we know that order of global stiffness matrix for this truss element is 2 into n. As we know that in our example there are 3 nodes. So 2 into 3, it is equal to 6. Okay. So the order of the global stiffness matrix for this truss element, it will be equal to 6. So finally, so matrix will become equal to 6 by 6. So 6 by 6 means u1 v1, u2 v2, u3. Sorry. So we need to map also. So u1 v1, u2 v2, u3 v3, or you can simply say 1 2 3 4 5 6, because we have denoted the displacements by u1 v1, u2 v2, u3 v3. Okay. Similarly vertical, for example u1 v1, u2 u2 v2, u3 v3. Okay, so this is your first element, this is your second, and this is your third elemental stiffness matrix. Now we need to map this elemental stiffness matrix. As in previous lectures for spring bar system, we have constructed our global stiffness matrix by using these elemental stiffness matrices. So same way we will try to construct our global stiffness matrix for the truss. Okay. So this element, the connectivity is in between node 1 and 2. So or between u1 v1, u2 v2. So first element it is mapped between these connectivity points. Okay. Second element's connectivity is u2 v2, u3 v3, or between node second and, so u2 v2, u3 v3. These are the columns. and U2, V2, U3, V3, these are the, so it will start from this point. Okay, so it will start from this point. Now third one is what? Connectivity is in between U1, V1, U3, V3, means U1, V1 columns, U3, V3 columns, and U1, V1 rows, U3, V3 rows. So U1, V1, I will just make this point C. U1, V1, U1, V1, U3, V3. Okay, this is the and rows V3, U3, V3, U3, V3. Okay, so this is the third matrix connectivity. So you can map these three matrices to get the or to construct the global stiffness matrix for the truss element. Okay, so in this way you can get your global stiffness matrix for the truss element. Okay, and we can solve. Then next procedure is same, means apply the boundary conditions. After applying the boundary conditions, you will get the eliminated equations. By using these eliminated equations, you will get the displacement values. By using displacements, you can get reactions, then stress values in each element. Okay, stress value or stress, the formula is same. Okay, we will see this during our example. So here up to this, we will get our global stiffness matrix. Okay, so in next lecture, we will try to solve the examples related to your truss element. Okay, so here I am concluding this lecture, and in next lecture we will try some examples related to your truss, related to your global stiffness matrix, how to construct the global stiffness matrix for truss structure, then how to apply the boundary conditions, and then how to get the displacement values. Okay, so here I will conclude the lecture. Thank you.